Hello everyone, and welcome to the video talkthrough for From Social Science to Data Science by me, Bernie Hogan. This is Chapter 4, File Types. So the topics for this chapter, first we want to understand how some data can arrive as nested rather than tabular, distinguish between the two of those. We want to be able to import some tabular data, such as a CSV file and an Excel file. Want to use a JSON normalized to make data frames from lists inside nested structures. We're going to show that with JSON, and then we're also going to show that as part of a workflow with XML later on. We're going to look at XML and HTML, and we're going to see how they use tags and attributes to encode data. I'm going to show Beautiful Soup, which is a library in Python I really enjoy, and it's one that can be used to extract data from XML and HTML. I'm going to show how sometimes Beautiful Soup and the tag extraction is useful, but sometimes it's more useful to just turn the data from XML into JSON using XML to dict. And then we'll spend a minute or two having a look at serialization, or the idea that you can take an object in Python and just write that directly to file, rather than using an intermediary like one of the file types mentioned above. So in the last chapter, I talked about a data frame and, really touted its, usefulness and how effective it is for analysis, but we don't really see a lot of data come into us as a data frame. Data comes into us in a whole bunch of different formats. Those formats come sometimes from software, sometimes from just the way that we measure the world. Often they can be in text files and not really of a particular format, but actually they can still be used and imported into pandas. So to make insights about the world, we might want to think that data has some sort of a structure to its measurements. And that structure can be a combination of something that's sequential. We can think of measurements as happening one after the other, maybe in time or just in some way ordered. We can think of them as associational. So, like your dictionaries. And we see here, like we might have a title and then get some value, or ISBN and get some value as well. And that would be a dictionary. And then we might have stuff that's hierarchical or nested. So we might say, I live here in Oxford, and Oxford's in the UK, and the UK is in Europe, and Europe's part of Earth. So we might see these as having a sort of a nested structure. And that nesting can take place where you can have associational things or sequential things, right? So within this value right here, we have a string, but we might as well have a list, and that list might have a dictionary in it. And this hierarchical structure really makes sense for transmitting a lot of data, but it's not very useful for analyzing that data. So files tend to have some combination of these, and you'll still want to get them into a data frame. So we're going to look at file types to show how we might do this for one data frame. Now the next chapter on merging and grouping shows how we would do it with multiple data frames. Now you might say, why not multiple file types? Well, because we get each file type into a data frame one at a time, and then we might want to merge them together, and then spit that back out to something else. And also in the next chapter, we'll look at SQL. We don't want to bother with that here because SQL really makes sense when we're thinking about how to extract or query from multiple tables and group them together. So before we get started in the chapter, I just want to give a little note on file organization. And I want to say just, avoid the downloads folder. And I know there's a real temptation to just get things from the web, just pop them in the downloads folder, and just work with it there. And in a chapter on file types, I think it's a good opportunity for us to not just think of like individual files, but how the files themselves are structured. So you'll notice in the book, and in chapters onward, I'm going to assume that the data that you have is in a sibling folder. Now, what do I mean by a sibling folder? We'll get to that in a sec. But the point of it is to encourage you to take things just out of downloads, out of the desktop, and to put it somewhere where that's going to be the project for learning in this book. And then you would want to repeat that for other projects and other things that you're doing with your code. So one of the ways in which we can talk about a hierarchical or nested structure is to use a family tree. And it's funny because with a family tree, the metaphor itself, like a branching tree, also means that sometimes we use tree terms like a root and a leaf. So the top of any sort of structure would be a root, and one of these bottom ones with no extras would be a leaf, but for the rest of it, it ends up being a family. So here we have here. So this might be any file or folder that you have, and above it would be the parent, and below it is the child. So it'd be a child folder, a parent folder, and then you can have a sibling folder as well. So if you had all of the code and stuff for this book in a folder like I do called book, then you would have chapters underneath, and that's where I keep the Python notebooks, and then data. And then there's actually also exercises there, and I'll pop them in there. And I actually have a lot of extraneous files that I use for things like converting the book to LaTeX and actually finding and replacing stuff. But for the sake of this, we put them in a temp right there. Okay, so if you have your files and they're not in the same folder, then you can't just say open file name and then it will open the file name. Instead, you have to kind of navigate to that folder somehow. And one of the old ways to do that is to use text. And so you would just write like dot dot, and that would move you up a directory. And then maybe slash just says here's the directory, and then you move on around that way. And that's kind of fragile. And one of the reasons it's fragile is because on Windows computers, the directory separator is a forward slash, and on Mac it's a backslash. So here we have it's the other way around. But that's that's part of the problem right there, is actually kind of recalling the distinction. But the thing is, people use both, and you're going to want to share your code with both. And so instead of using a literal slash back or forward, we can use an object, and the object in Python is going to know whether it's forward or back depending on the operating system it's on. So pathlib has that available. And pathlib creates path objects. And, path objects work like the plain text, like just navigating to the path. But instead, they're instantiated as objects. And by being instantiated, they have methods that you can do things with, and they have their own syntax. I know having its own syntax might sound like we're adding more complexity to this, but actually it adds a lot of robustness and a lot of clarity for how you might work with it. So here we have an example. Here's how you would instantiate a path object, path, and then just write the directory in there. And I called it P. So here we might say if the path to the data directory is here, you might just write here's the path, and then that'll create a path object called datadir. Now that's all well and good, but maybe you have it in your computer and you don't name yourself work, or you don't have it just under documents. You might have it under a different name. So how can we make it a little more general than this so that I could share it with you and you could share it with others and not hard code the path names? Okay, so let's just start from here. So the current directory, wherever you're in for like the chapters for your code, just say CWD, or current working directory, and then that'll return a path object that is there. And then you can use other path object details to help you along. So for example, parent is the directory above, so we can do this and go dot parent, and then it'll go here, and then the parent above, or the directory above here. And then once you're in that directory above, you can use this slash here and this backslash, this slash here, and it works as a separator regardless of operating system. And this is the Unix separator right here. And then you just use the name, but you put it in quotes. And quotes works nicely there because sometimes a folder name has spaces in it, and if you put it in quotes like here all the time, then you don't really have to worry about that. So to get from the current directory, if you have your notebooks in one directory, to a sibling directory, we go up and then down, just like what I've done here. Datadir equals path, and then get the current working directory, go the parent, and then go down to data. And we can see that over in Jupyter, and that's the first bit for today. Okay, so I've started here, and so this is the first thing we do, just import pathlib. And here I've set a data directory, and it's where this file is in one up, and I can show you that right here. So if I go book, and there's the data directory right there. And so I'm going to go back to chapters, And here we are. So it says if datadir exists, if it doesn't exist, then make it. And so you can see how a path object now, you can use it to do operations on the file folders. When I first learned this, it also made me a little bit spooked actually by the sort of permissions that you can get for these sort of files. And for that, I want you to be just a bit cautious about making directories or deleting files, because Python can be very powerful, and you don't want to accidentally do stuff where this is deleting it. It's not going to go into like a recycle bin or something. It could be just gone. So with that being said, if it doesn't exist, you can make this directory and put your data in there. Okay, and so in this case, we can see where the path actually is on my computer. So I put it in a GitHub thing, and here's the directory for when I'm working on the files. All right. So now that we have a way to access these files, let's have a think about kind of what sort of data we want to get into a data frame and how to do it most easily. Well, recall that tabular data is structured with rows, and the rows represent cases or observations, and they might have an index, or you might just a data frame will create one, but you might have one. And then you have columns, and these would be representing variables or features depending on how you name it of those cases. And they might also have optional column names or like a header, which would have the column names. Oh, and see here we can see here an example in a text file of just what might be a CSV file. It's comma separated values file, and you can see like this is a really common structure for here, where we would take this as a table and then pop it right into a data frame, and you can do that in pandas with pandas.readcsv, and there's the file name right there, and it'll know that. Now, it's worth noting also here a difference between a file name, which would be a text string, and a path object. If you put a path object in there, it'll work just fine, just the exact same way. And it'll also work with a file opener, but we don't normally work with that with readcsv, which you can just put the file name in, or a path object, as I'm inclined to do. And when you do that, then you can get a data frame, and it looks something like this. Now, I want to just give a little moment here to Gonzo. We mentioned in the last one, I think I used species whatever, sort of thing. Well, it's right here that it's missing. But even though it's missing, then what Pandas was able to do is give that just like a missing value, a null value, and then all the table here is nicely aligned. So a CSV actually we might think of it more as a convention rather than a file specification. We didn't have to say none or null in here. In fact, it can be a bit messy depending on where you get your CSV from. You might be replicating someone else's data or their analysis, and they'll have it in one way or another. But the readcsv method is actually pretty flexible. There's lots of optional parameters for things like making sure that you got the right quotation marks in there, or whether it's actually tabs that separate it rather than commas. And so we can see a little bit of that over in Jupyter. And I'm not going to go through the full example right here. You can see that yourself. But what we do see here is I import CSV. And this is the CSV library, which is one that's not in Pandas or not Pandas specific. And you can do that to get the CSV written as like a list or a dictionary or so forth. And then down in Pandas, we can roll all of that into the read CSV right here. And here you can see I use Muppet table fixed. Now, if you go through this right here, it's a little lesson on how the quotation characters you have to be pretty careful with, so that you know which ones work and when. So a CSV is just like a text file of comma separated values. Might have some little variations there and so forth, but there's a lot more complicated file types that you can import into Pandas. One really common one would be Excel files. It's really, it's just common to see a lot of data come down in Excel, be stored in it, and transferred that way. And also I like starting here because unlike some other file types or ways of getting data, it also really emulates the data frame. And so So pandas can read and write Excel files, and that's really also handy for shipping stuff. Oftentimes, you might be working with people who don't want to, fire up a JupyterLab notebook, or you don't really also want to go as far as like creating a web app or something to show some interactivity. Just give them Excel file. And that can often be the simplest. And you can also use open source products as well for the same thing, and Excel does tend to read them and so forth. Now, if you're using Excel in a data frame, you have the read Excel and write Excel method. So that would be like pd.readExcel, and you'd put the file name in there. And same for pd.writeExcel, and you'd put the data frame, and it will then, and the path, I believe, and it'll send that along the way. So now, so here's some tips for the Excel package. You can set an index, so you can take the spreadsheet that you have in Excel, and you can let the reader know, is the index in column 0 or is it in column 1 or so forth. And you can also say whether the header is available. Now you'll notice header equals true is the default, so it will infer that there's a header if at the top. So read Excel can read up to any row or column in the first sheet, or by default it'll just try to find all of it in the first sheet. But you can set which columns you want to read, or which rows you want to skip, and so forth. And so you can be quite nuanced with what you do in terms of parsing in Excel. And now, even though you can be quite nuanced, there are still some limits to it. And read and write Excel will not include formatting or create formulas. So if you have an Excel sheet with, say a ledger of something, and you have like sum or average at the bottom, then when you export this, it'll export the value that shows up in that sum. It won't export, equals sum and then some formula. So you got to be cautious of that if that's one of your goals in using Excel. Now, fortunately, other engines and libraries like XLSX Writer, that can preserve the formulae in Excel, or read and write other formulas and stuff. So you can really scale up the complexity of this. But the important thing to note is that you can, import it into Python. I go through an example of that in the book and in the JupyterLab, but I think we can kind of get the picture here. I really wanted to move on to nested data, because nested data is much more common in the web in some format or another. I also want to give a hat tip here to the paper Tidy Data by Hadley Wickham, who explains with some nice analogies and nice detail about how we would want to think about the difference between data that's structured in this way and why we put it into tables, and why those tables we want to link them together. But for now, let's just think about data out in the world. Now, this is a stylized example. If you look at the current Twitter API, tweets don't come down like this anymore. But this is something like the way that tweets used to come down as JSON, but it's a bit simplified. So we can see here, this is an actual key in a tweet. So it's tweet, and then it's the text of the tweet. And then we have likes, and this is a number here, just 32. User, and you'll notice here that user isn't a value, it's a dictionary. So it's that nesting that I was talking about. And under there we have two kind of primitive objects, we might say, just the integer and another string. And I refer to that in that way because it's different from down here. Under here we have yet another dictionary, and this dictionary has a list in it. And so that's going to be a bit relevant later. We'll show some important details about the fact that what happens when we get lists nested inside dictionaries. Okay, and so this just kind of describes it there with the 4 top-level keys and so forth. Now, this is the way of nested data, and we might say, how do we get from here to tabular data? So we can start by thinking of that, with JSON. That was JSON, that object. Now, JSON stands for JavaScript Object Notation. And it's commonly used as a format for data transmission and sometimes storage. For example, in Mongo databases, you can just store stuff as JSON, and you can query it that way as well. So the file can be read by a text file reader. So you can open up JSON and you can look at it in a text file, and you'll see data in some combination of dictionaries and lists. And it's very similar to a Python dictionary. But it uses some different literals, for example. So in Python, we have none, true, and false with these uppercases. And in JSON, we have null and lowercase true and false. So you can't just literally make it a dictionary, but it's very close. So you can kind of treat it like that. And how do you do it? You use the JSON package. And you can go json.load or json.loads. Now, I don't draw attention to the distinction in the book, but JSON, this S here, refers to a string. So if you do loads S, then it expects string data. So the JSON that we saw in the over here, it would be like you put that in quotes, and that's a string, and it will parse that. Whereas load expects a file opener. So that's like, where we would open the path name of the file, and then you put that into the method right here. Normally what I do is I actually just take all that file opener stuff and make it into a string myself, and then put that inside json.loads. And I don't know, I guess the reason I do that is because I like the way I can use the file opener to manage things like the encoding, whether it's UTF-8 or something. Those are weird little details, but they do pop up from time to time and make it a bit tricky to parse files. So if I just then always ensure that we're expecting a string, it doesn't matter how it gets into that string. So now how would you get data back into JSON? Let's say you have some dictionaries and some lists, it's some nested data, and you want to get it into a JSON style. Well, then, you would use json.dump. And the same thing right here, dump would take a file opener, and dump S is what you would do to make it into a string. And then maybe later on, save that string or print it. If you don't set any options, it's just going to make it one wall of text. So what we can do instead is use the indent parameter. If you go indent equals 4, then every time in the nesting, it'll go down by 4 spaces. And so let's have a look at that over in Firefox. Okay, so I'm going to import JSON here. And what I've used is the Muppets again, of course. And I went to OMDB, and this is the Open Movie Database. It's just a database of movies. It's not. It's more open source, I suppose, than Amazon, and it has a very, very simple API, and so that's nice. So I use that API to get the search queries for Muppets. And what we have here is the first page of the search queries. Now, if you iterate through that, and that's called paging, something which we cover in Chapter 6, then you can get the rest of the search queries and build a full data frame out of the multiple different instances. But this is just the first set of search results right here, and let's have a look at it just as text. So you see what I've got here done, json.dumps and indent2. So each level of the hierarchy should be about an extra 2 spaces in. And I'm not going to look at the full string. I'm just going to look at the first 300 characters. And we can see that. And why the first 300? Because we can kind of get a sense of the structure from here, and then I can go on. So we see here, here's one, The Muppets Christmas Carol. And so that is one entry of these search results. And here's another one, The Muppet Movie, back from 79. Now we can see here the indent equals 2, like so forth. And we can also see that this is inside a list. And so because it's inside a list, that makes it really useful. These are just results. And those are probably the things that we're going to want to put into a data frame. But now you'll notice this mdata. This is the JSON itself. Let's just have a look at those keys there. Actually, it has 3 keys: search, total results, and response. Now, this is search. We had a look at this right here. But let's have a look at total response, or total results and response. 62 and true. Okay, so it doesn't really seem like the data that we want. It turns out these are kind of operational parts of the JSON that are used so that you can find out later on, well, if I want search results part 2 or 3 or 4, how many do I want? Well, there's 62, so you want maybe up to, 7 individual queries, and then there won't be an 8th query because there won't be a response number 70 or 71. Okay, so now we can see if we print search 0, it should probably return this right here. And there we go. And now we can, of course, then preprint that. So we had a sense of, how data can be encoded in a JSON file, and that sometimes in those JSON files we have lists, and those lists can be things that we would want to put into a data frame. So how do we do it? Well, JSON normalize is a really useful command for that. So where JSON has a key and the value is a list, is a good opportunity to import it with a data frame. each element of that list is going to be its own row in the table, like each search result or whatever. And so this is done with JSON normalize. So you normalize the value that's returned from what you pass to it. So let's see here. If we look at a tweet object, now remember in the slides here we have this this tweet here, real simple one. Hey, I like Twitter, and so forth, right, like that. Now what happens when we try to normalize it? Go over here, and we get one row with 5 columns. That's okay. 5 columns? We'll see now in a second. Okay, so what happened was we got one for tweet, one for likes, one for user.id, and one for user.name. And then we have one for entities.hashtags. Okay, so now why did it do that? That was kind of interesting. What happened was it kind of went down because they're, like I said, primitives. It just said, well, we'll just make that its own column. It's kind of simpler that way than trying to make this and then put a dictionary in there. So it kind of infers that maybe it can be a bit too smart for its own good sometimes, but actually it works pretty well. And we'll revisit this again in Chapter 6 on web data, where we download some data from Reddit. And you'll see how the column names are a result of this JSON normalize trying to be a bit smart along the way. Okay, so here we are. And, since it only had simple values, like it did that. Now, if you do this for tweet and the user, then you'll see it takes those columns and it doesn't have user dot at it. It's just ID and name, because remember, it's normalizing the value that's returned right here. And also, you notice that entities.hashtags had its own little dictionary in there. So if we normalize by that down to the hashtags, we see name. It's got 2 names there, but it figures out that name is the column, and that artsy and design are the hashtags, and thus they're the rows in this data frame. So you can see how it does this really nicely, and it's actually I find a really useful and handy thing to do. So I've here come up with a very simple dictionary right here with some made-up movie names, and just see how we see what they look like when we normalize them. You can see, figure out title was a column and year was a column, and so here we have our data right here. Now, if that Muppets data, that JSON data, that's a little more involved, let's have a look at this. We're going to normalize that as well. And also what you'll notice, see what I've done here, is I'm not going to display the whole data frame. I'm just displaying the first 3 columns. If you want to see the whole data frame, we can put that there. And there we go. And you'll notice it has these extra columns right here, but I didn't think they were worth showing, and I actually did think it was worth showing the fact that you can truncate your data frames like that. All right, and so here we can just see what happens when, instead of normalizing by the whole thing or by search, which has the list in it, instead if we normalize by like just the JSON, it puts the whole search thing in this one cell right here and gets total results and response. So that's not really what we want. It wouldn't really be very useful for doing analysis the way that this would or could be once we clean the data, doing things like cleaning out this difference right here. So JSON certainly isn't the only nested data out there. I mean, one really, really common and prominent form of nested data is HTML, or hypertext markup language. And it's also really common in a thing called XML. XML might actually be more prevalent, be more common than HTML. It's just behind the scenes. You wouldn't really notice it. Now, both HTML and XML are markup languages. So what they do is they put some text symbol on either side of a value to mark it up. And we do that in other text as well. So this is marking up. We use these little icons right here to say this is a quotation, like this, he said. So markup languages, they're, HTML and XML are pretty similar in form, and but HTML has these very specific tags. So now in the general thing, what you would have is these tags with these angle brackets, and then you would have the name of the tag in there, and you can have a closing tag as well. So inside that tag, you can have some values, you might have some text, or you might have more tags. And so the tags can nest really deeply in there. Now, if the tags in HTML have special names that refer to things about, it's a browser, it's a link, it's JavaScript, it's the shape of a table or something, whereas doesn't have XML doesn't have like specific names that you would put in the tags. It's more just like generic. It's how you put that structure together. However, there are extensions to XML. In fact, we might argue that HTML is one of those extensions. A different extension might be GraphML, and that has like tags for nodes and for edges and for graph properties. And so if you're doing network analysis, using GraphML is really useful for storing your data. So it's often common for us to extract data from XML or from HTML. Like we're going on a web, it's a web page, and it might have a table or a link or some text that we care about. But with XML, we often see that in terms of data storage or data transfer. It's a really useful example where we can kind of compare the HTML and the XML. As Wikipedia, you might know this. And here's Canada. Here's where I'm from, and this would be the URL for that. Just Wikipedia, /wiki Canada. And if you look at it, right click on the browser or press, I think probably F12 in some browsers, you'll see it as HTML. And this is kind of a little bit of a crop here, what it might look like. You'll see it's nested, so it starts with HTML at the top, and then underneath is a tag called head, and in head is a lot of useful stuff in JavaScript and that. Then it'll have body, and body will have like the things that you see in here, and then the tags will close. But you can also export the data. So that's the data you export is this stuff right here. The coordinates, that it's featured, and not just all of it the way that it's rendered on the page, but the important details as data. And so that's what it would look like here. Now, notably, this here is it's XML, but it does have this schema in it. As I was mentioning, you can extend XML so that you have special tags for your particular kind of data. And in this case, we have MediaWiki, which will give us some very important or specific tags that we would expect in a file that would come out of a wiki, or specifically Wikipedia. So now, how would we navigate or parse this? It's not JSON, so we wouldn't necessarily use JSON normalize or right away. Well, one way we can do this is using Beautiful Soup. I really like Beautiful Soup. Sometimes it works out really well. Sometimes I'll use other approaches. But let's give a sense of this. So it's a useful library for extracting data from XML and HTML. And what you do is you give it a parser, and it'll return an object, a soup. You can call it soup, which you can then query by tag, much like you would query a set of nested dictionaries. Now I'll show a little more of that in a second. So here's what we would do. Here's soup. It's Beautiful Soup, and let's say this right here is just the string. So you read the whole file in as a string, and that's what this will represent here. And here's our parser. We're using the XML parser. That should work really well and get it into a soup. So now it's more than just XML and into a nested dictionary. And by that I mean, if we go back here, and we see this, like, it's not just that it'll turn this into a key MediaWiki and a value the rest of the stuff, and then a key site info, and then a value all the rest of the stuff. It's actually a little more clever than that. So one of the things that it can do is that you can reference any tag regardless of where it is in the hierarchy. So here we have, like say, our soup object, and we saw there at the top was HTML, and then body, and then MediaWiki page. Oh my goodness. Revision ID text. Now this is what we would use to get the specific revision for a page. So every time someone changes something on Wikipedia, it's going to create a revision ID. But fortunately, we can just skip to soup revision ID.text. Now, why not just soup.text? Well, because text would be the first text, and much more. I think it would just be everything. Can we just say ID? Well, we could if this was the first mention of any ID tag, but it's not. There's actually another ID tag up there. I think it's like the user ID tag or something. So but it is the first and only tag called revision. So once we use revision, then we can go down from there. So it's a bit clever in a way, and it might be a bit tricky. You might not necessarily want it. But where this is useful is particularly with things like A tags, because an A tag refers to a link. And so this would be a hyperref or a link within the web page itself. And so often when we're doing work with HTML, we want to know not just the text on a page, but where that page points to. And so iterating through the A tags wherever they show up in the document can be really useful. You can also use this to strip out HTML or strip out all these extra extraneous bits from text, because this text right here will be all of that with the tag stripped out. So now in chapter 10, when we look at the Stack Exchange data, all of the comments that are in the Stack Exchange, they're all written and encoded with HTML. So like when you go on a Stack Exchange page, it will it'll have things with like nice little URLs with blue links and nice maybe tables and stuff right in the answer. Well, that's all in there, but it's all kind of extra gunk potentially if you want to do a text analysis on the post itself. So Beautiful Soup would extract that. And so we can have a look at it in Jupyter right here, and we're going to go down to okay, so here I was just showing Wikipedia as HTML, and here's it's a lot of characters. Here's what the top of it would look like, and here we have Beautiful Soup. Now you'll notice that I loaded this as a string of data, and so here's the first couple hundred characters. And so I call it Wiki HTML, and I can use the HTML parser. I believe that is the default parser. We can check, but it is worth being specific about these sorts of things. Now you'll notice down here, like I said, how you can query for tags. So I'm going to query for all the A tags and see how many are in there in this file. And so sure enough, here's the text of the file title. And how many A tags? There's 4,300. So on that Wikipedia page that you saw, for Canada at least, it's a lot of links, and there's a lot of mess to those links. And so while not in the slides, I do talk about in the book some data skepticism, how we might go through those links and check which are URLs, which are not, and kind of just see how we can be a bit careful with the data. Now for here though, I just want to move on to XML, and we can see how long is it. Well, it's this many characters, and here's the front of it. So it's like it's a string of data that we got from a file with these nesting tags. And so once again, we can import it. Now you'll notice one thing that I did here. This is this I had to discover for myself. In the Wikipedia XML, they use a tag called text, and that's not really very helpful if you want to query the text. So you'll notice that over here, what we wanted to do, we got soup.revisionid.text. Now that wasn't a tag, that was just like the text in between the tags. So what happens if you have a tag called text? Well, then you're going to run into trouble. It's going to get confused. So I did this replace here with text, and I made it called Wikitext. So now we can query a tag called Wikitext, do the same sort of thing, and it's not going to get in the way in our data. I wouldn't normally go through in detail all such little fussy matters, but it is worth noting that these tend to crop up in places here and there, and they can be very frustrating if you're not used to them. But the nice thing is that when you figure these out, then it's you can just make one line of code here or there, put it in, and then run it as usual. So I'm going to run this here with this, and if you'll notice the replace statement that's in there. And we can see that this is now the revisionid.text. Now you can navigate it, and this is kind of going through the same thing I did before, the revision ID, and how you can go really far down or just ask for it quite directly. So Beautiful Soup is not the only way that you can parse or interact with an XML document. Python has a built-in library called element tree, and that allows you to navigate that tree that we were discussing earlier, whether it's a tree of paths or a tree of HTML or a tree of XML, depending on the parser that you use. There's also an XML to dict library, and that's XML to dictionary. And the reason that it's available is because sometimes we want to do something kind of simple, and Beautiful Soup might overcomplicate things for us. Now, when we parse HTML, we're usually looking for relatively unstructured data. We might be looking for links here and there, and so iterating through tags is a useful thing. But XML tends to be structured data that you just want to put into a data frame. And now we can see here as an example, here's the Stack Exchange data, and this is the movie data that I use later on in the book. And if we see, it has a bunch of lines here. Each one is a row. Each row has a value. This can be an index or some column of data here. Now you know that not all of the same rows have the same columns of data, but that's not necessarily a problem for Python. But the point is that this comes in, and this is a list. And it's a list inside could be inside a dictionary where this is the key and this list are the values. So we can do that in JSON. We saw that in JSON. Why don't we just turn the XML into JSON? And so XML to dict does that. And so we can see an example of this on the next page. So let's have a look at this right here, and we can see example as HTML, as XML. It's a really simple one. And here's what it would look like when you convert it to JSON. And these right here become kind of this list and dictionary structure. And then over here we can see how it would happen if you use JSON normalize. And just like before with the Muppet data and so forth, if you do it at the root, you get it this way. But if you drill down, you can get to the list, and then it'll normalize the columns. Okay, one of the last topics I want to cover for today is serialization. And so this is called pickling in Python. So it's like you pickle your object in a jar, I guess. But serialization is useful, and it's in a lot of languages and using different terms or libraries. Now, a data frame, as we pointed out at the beginning of this lecture, it's a Python object. Well, I guess we knew that, but also that it's an intermediary object. It's like something that we do with data when we bring data into Python, but then we work on it in the data frame, and then we send it back out in some way. Now, what if we want to just keep it as a data frame object? We don't want to export it. We're not sure the way that we want to export it. We just want to keep it just nice as it is. Well, you can do that, and what it does is it serializes the object. It writes it as a series of bytes, and those bytes signal both the data that's in the data frame, all the stuff that we put in there, maybe also some features about a data frame that are relevant, maybe the sort order or what the headers are, et cetera, et cetera. And so in order to serialize an object, we would pickle it, and we use import pickled, import the pickle library. So the text in the pickle is it's not quite human readable. You can open up in a text file and it'll have some data that you'd recognize, but also some other stuff as well. So because it's not decoded text, it's an encoded byte stream, and it's slightly different because byte streams are more specific for maybe what you would see as an emoji, and in a byte stream it's like /x32, /x41, et cetera, et cetera. But the computer wants to store it in byte streams, and the serialized object is a byte stream object. And so the one thing that I wanted to point out here is that when we create a file opener, normally we would use R for read a file and W for write a file, but here we want to use RB and WB for read and write byte streams. So here's an example of how we might see a pickle. So I call this df1. It's a data frame. It's really simple. It's like 1, 2, 3, and then 4, 5, 6, like a table of 2 by 3. Okay, and now we see some syntax for writing it to a file. I kind of like this syntax here with open WB as file. So this becomes a file opener. So this is a file opener for this particular file. Now this is a bit bad form. All that stuff I said about going in the data directory, and here I am dumping it right in a folder, but that's because it's on the slide. And so we can see here, then I go pickle.dump, and I put the file, the data frame right here, and right here's the file opener. So we just drop that in, and it's pickled. And then we can load that file again. You can see pickle load, and here's the file opener right here, open blah, 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 blah. It's got read bytes. And you can just check, does the first one equal the second one? And it'll say true. And so let's actually go and have a look at that over in Firefox. All right, so if we go down to serialization here, import pickle, and you'll notice here I do an example. The example is it's just a dictionary. I didn't actually even bother with the data frame, but just put that in. Now, one thing I do want to point out is that what you pickle is a single object, but that single object can be like a list, so it can be a collection of other objects. So here we can example here, I put data example, and I popped that dictionary in there, and I put other data as another example in the list, and so forth, whatever. And what I do is I dump that data for pickle, and then I use this path right here. And this time I did, in fact, dump it into my data directory right there, saved in my data directory. Okay, so now once I have it saved in there, then I'm going to go and I'm going to load it again. And so we load it, and here's the file opener once again, like this, and we're going to print it, and it should have this dictionary inside with other data and that pi-like number. And so there it is. You might want to actually make use of pickles, for example, when you are collecting data from the web. It's really useful for robustness because the data collector is often waiting for something from a server, and something might go wrong. And if something goes wrong, maybe you want to save the data right where it is before then going on and throwing an error or doing something else. It can be a bit advanced, but it's also really handy. So there's other formats and approaches to file types other than what we've seen here. And here's some other use cases. We can think about databases. We're actually going to discuss them a little bit in the next chapter, relational databases. But there's all kinds of databases for different uses or purposes. One like Mongo, which I alluded to earlier, stores data as JSON. So it's like JSON as a database itself. Others, there's graph databases and so forth. Now you can have longer term archiving for large data. That's not quite the same as the way we do with the files here. And you might want to use file types like Feather, which are useful for having really compressed data frames, but yet are easy to open. Now data can sometimes come down in streams, and mentioning that above. So if you're listening on a Twitter stream, you're effectively waiting for new data, maybe using a certain hashtag, and hashtag vacation. And every time someone says, "Gosh, I can't wait to go on vacation," it comes down. But otherwise, the program is just waiting there. Well, that you wouldn't want to necessarily build a new data frame every time new data comes down. So there's ways in which you can explore that and see about how you save things in streams. And then at periodic times, maybe put that into your data frame and do your analysis. So it's worth noting that Pandas accepts zipped files as well. So if you get a file like a database, the IMDb database, for example, comes down as a zipped file, and you don't need to inflate that zipped data in order to use it in Pandas. And that can actually be handy because it can also save memory space as well as save space on your hard drive. So in summary, thinking about file types, phenomena can be structured as data in a whole number of different ways. If it's structured in tabular format, it should have rows and columns, which is like a data frame, so it's pretty easy to just add that in and see what it looks like. We tend to assume then that each column also has a similar data type, and it should have names and headers. So when we put that in, we're already making assumptions about the structure of that data. CSV and Excel are tabular, and they have these features. The default read CSV and read Excel work, but you might need to tweak some parameters even then to make sure that you've got the data in the shape that you want. Now there's other formats that we mentioned, particularly JSON, HTML, and XML, which have a nested data structure. So they have tags inside tags or lists inside of dictionaries. Now we can navigate those files when we're parsing them, and we can navigate them as if they're dictionaries in Python, or we just import them into Python and work that way. But they might need a little bit of finesse. We might want to use Beautiful Soup. We might want to use XML to dict, and find the easiest way to get that into the data frame that we want. Now once we have it in the data frame, we might want to just save it, export it as is, or we might want to do other things with it, and some of those might involve pickling it or archiving it in a nicely zipped or condensed file. So here's some questions you might want to consider with file types. It's fun now that we're getting more towards the wider web. We're going to get out there and look at some interesting stuff. So we can do that now that we have an understanding of, this series, which collects a distribution, and we can ask questions about it. The data frame, which puts all of those series in a single aligned order. So we have cases, and each case has some values about it. And then we can think of the sorts of data files, data types that we can put into that data frame. So out on the web, the data is in those file types. Here's an example, and not to steal too much of the thunder from the chapter 6, but if you go to any Reddit page, you can get that Reddit page as JSON. So by just typing api.reddit.com instead of reddit.com, and it'll return that as JSON. So you can try that with a subreddit such as the subreddit, and that's a subreddit for like cute pictures of cats and fluffy things and whatever. And so if you go there, you can get this not just as text or HTML, but you can get it as JSON. So when you have it as JSON, if you just go there to the page, you might see this. This is what happens in Firefox, and in other programs, there's something like this. Now, what's happened here is that we've navigated to here, and it says JSON, and we can navigate the data like so. And children, and each one of these is going to be a Reddit headline, probably some picture of a cute cat or something like this. Who knows? But now here's what the raw data looks like. It looks like this. And so this isn't very pretty printed. This isn't like the stuff we saw on the slides. But it is if you want to pretty print it. We can click on it and look at this, and you can see the structure. Now this structure will also show us that the JSON kind of makes sense, and it has a whole bunch of details. So it's a bit further along than the JSON that we saw in this chapter, but it's not going to be long before you're going to want to parse this and extract some interesting data from it. So you can take this and you just save that as JSON, and you can read it in just like the JSON that we've seen in these Python notebooks. Okay, so if you do that, can you turn it into a data frame? Well, I mean, you can skip ahead in the book and find out, but why not have a go with the skills that you have right now? So now the way that I've shown the Wikipedia data here and in the example in the book was I used the special export web page now, or the special export command. I say that because you can use this command through the command line to do some really nice, neat features, but you can also do it through the browser as well. And over here in the browser, we can see this is that URL. It's the export page, and you can add a page right here. So I could add a page, Canada. If I do that, I export only the current revision, and that's what we saw in the slides. Now, if we uncheck this, it's a 22 megabyte file, and that has, I believe, the most recent 1,000 revisions to the Canada page. So it's a big XML file, bigger than the one that we saw in the example here. But same question. Can you make that into a data frame? What would you put into it? Would you put the body for the Wikipedia for every one of the 1,000 in its own cell? Would you extract some text from it? Would you just get a series of the revision IDs for all of those and make that its own distribution? So that can be a bit tricky, but once you do that, then you can really start to see some interesting features. Like over the last 1,000, what links went in, what came out, is there anything that's disappeared? And Canada's, it's a country and there's politics and so forth, but there's all sorts of other ways we can consider this. One example that I did in a class one year I really liked was we look at the article on data. Now you might remember from chapter 1 that I mentioned DIKW and both problematized it, but also showed that it might be an interesting way to think about data. Well, DIKW, interestingly, appeared in the article on data, and then it disappeared. And then a few years ago, it reappeared. So it has kind of an interesting story in relation to the article on data. Now, we can start asking about that story because we can get all of these different XML pages and then put them in that data frame. Now, the sort of ways in which we would do that involving visualizing and other stuff, we'll get to later in the book. But already we can start to see how we can make distributions of things, and then start asking questions and making claims about them. Now you can also load a data frame from an Excel document, and one thing I'd like to consider with that is when you write it back to Excel, have a look at it. So I used the example of the World Bank in the in the Firefox, sorry, in the Jupyter Lab notebook, and the that's kind of like the data as it came down from the World Bank's Data Explorer. The Data Explorer is pretty thorough, but then if I load that data into Python and I write it back, it doesn't look quite like the data that I got from the Data Explorer. Some stuff is stripped out. Why not try that yourself and have a look and see what's there, see what's missing? And that helps give you a sense of what you have to specify in Python if you're going to work with Excel data. And then finally, what about other formats that you might use for statistical data? Do you use stata files? Have you ever used them? Or SPSS.save files? Do you think these can be imported in pandas? How do you think they could be? Why not have an explore for that, and you might be pleasantly surprised. So that's it for the chapter on file types. I hope that helps us, start to get off the ground and get some data in, and so then we can get some ideas out. Now, the next chapter is on merging and grouping. Thank you for listening.